All right, in this video, we will cover a new lab. All right, this is the NSL-KDD lab. So NSL-KDD is a data set that has been created for network intrusion detection. So in another video, I will kind of describe a little bit more of the details of the lab, but in this video I'm just going to focus on the code and solving this with Tensorflow and with a GPU box. So this is our big data lab. Then the data set that we're using has over 4 million records. All right, so that requires, so we will not be using this, solving this one with Weka, obviously, because that would run out, Weka would run out of memory, and we benchmark this with sklearn, which is also slower. And so this is a perfect example. We have 4 million records, so that certainly I would describe as type of big data. And so we will look at several things, several considerations now that we have. Since we have big data, we're going to do batch processing with Tensorflow, so that will be new. The code will be very similar to the code we've had for Tensorflow in previous labs, like the one we had for the malware analysis lab. All right, so the code will not change considerably. It'll just be a few additions now for big data. But in essence, as I said, this is network intrusion detection. So there are about 40 features. These are network features coming from packet headers, the IP header, TCP header. So those features, we won't extract the features from the raw data in this lab. It's 4 million records, so we already have the data set. The data set has basically the labels, which are either normal traffic or attack. So there's more than 20 different attacks there, like denial of service attack or session hijacking, those kinds of things. So what we're going to do is, this is a choice, right? You could have multi-class problem where you have one class is the normal traffic and then many classes that are individual attacks. And you'd have a very imbalanced data set. But we decided to make it balanced, so we took all the different attacks and basically just pulled them together into one single class called, not normal or attack. And then everything else that's normal traffic, like, web browsing or something like that, that is just one category. All right, so this is a two-class problem basically, and we have about 40 features. Which are the regular, if you look at the IoT devices lab, for instance, very similar types of features as those. All right, and so, but as I said, this is big data, so it's about over 4 million records, and so we have to do some additional things. All right, so I'm already logged into my computer here. This is one of our GPU boxes here on campus. We will also do this with AWS and just show that those are also GPU boxes. The idea, GPU boxes, they're Linux boxes as well, so you log in just like you do normally. Then usually after that you have to use the source command to kind of load the environment. So we want to load the Tensorflow GPU environment. We've already configured that so the GPU runs by default. All right, so we don't have to really do much, and just the GPU is going to be the one that does the heavy lifting here for our matrix multiplications. Right, so let's go ahead and first of all load the environment. So I'm going to do source home powers, and then we are using Anaconda, and then bin, and then we activate. So we are using Conda to activate our virtual environment. All right, so activate our environment is called tf-gpu-cuda. And I recommend that you do something like this. So, this is, if you don't know what Conda is a program that you can use to upload several versions of, let's say like programs. So you can have Python 3 in one environment and then Python 2.7 in another environment. So it's very useful in that sense, and it allows you to configure things by default. So you only use specific libraries, GPUs, etc. So in our case, we are loading this environment. All right, and there you go. So now I have my environment, so I'm there. All right, and I'm ready then to run TensorFlow for GPU. All right, so the first thing is let's look at the directory. So I'm already in there. This is the directory. If you're following along with the labs, you should have these files. Remember, you can always get these files from GitHub, or you can get these files from our website, or on Clark if you're looking for them in Clark. So the important things are we will provide this data set already. This is a really large data set, so we didn't really want to have you do too much processing on it, since the learning objective of this lab is really to be familiar with the big data issues. So we've taken care of a few of the things. So the other important script that you need is this one, KDD tf.py. So that's obviously the TensorFlow script. So we provide this starter code for you to do. So again, the lab here, also the code, I've already explained this in the lectures, right? So if you're following along with the book, this is in chapter 4 towards the end. If you're looking at the videos, these would be all the videos related to linear regression, logistic regression, neural networks, and deep neural networks. So the explanations of everything in the code and the theory is there. So as I said, this is a lab, so I assume that you've already looked at those videos. And today I'm just going to focus instead on the code itself. All right, so let's go ahead, and the first thing we can do is we can look at the data set. All right, so I can do something like cat KDD cup, all right, and we can just run it, and you can see there that's our data over there. You can see ICMP packets, TCP packets, the product, the services like HTTP are there, and individual values, and features to use. Okay, so that I'm going to kill that. All right, so I'm going to do it clear. So that's the data set. If we want to visualize the number of records in the data set, we can do something like WC-L and then KDD cup, all right, CSV, and then so according to this, we have about 4 million records. All right, so 4,898,431. All right, so that's a good size of data. So that's a good size of data there. So now the next step is we are going to look at the script. So I'm going to open up the script, and I'm just going to modify it a little bit as we go along. So we're going to open up KDD_tf.py. Keep in mind you can use any editor that you want. I just happen to be used to Nano, so I always use that. Now you can see here these are the libraries as usual. Import TensorFlow as TF, NumPy, Pandas, and then a few other things, gen from text, right, which we've used in the past for loading data. sklearn, we're still using the metrics from sklearn. That's just a choice. We built that nice function, so we've been using it quite a bit. Matplotlib is also there, all right, which we will be using for graphing purposes. All right, so let's look at some of this information here. All right, so I'm going to start typing up here a few things. Now, in this lab, remember, consider this your big data lab. We're doing NSL-KDD, which is a network intrusion detection data set that we already have it ready to go in the sense that we have our data. It requires very little cleaning. We have the classes and the features already identified. So here's the learning rate. What I would suggest for the student is to play around with this learning rate. Try other ones like 0.01, 0.1. So here, because it's much larger, this will start to have an impact, right? So remember, this is the step size that the giant takes over a mountain range. So try different configurations. All right, as far as the number of epochs, we may not need 5,000, right? So what I would say is leave it at 5,000 here, but I'm just going to try 1,000, right? And just see how that goes. Now the batch size here, notice that I have 100,000. However, I'm just going to start with 100. So that means, think about what's going on here. You're going to take 4 million records using the CPU, not the GPU, and you're going to take, in a for loop or something like that, out of 4 million records, you're going to take 100, then 100. So 100 at a time you're going to be loading into your TensorFlow code. So let's see, what that does, right? And then after that, I would suggest that you consider, okay, trying batches of bigger sizes like 10,000, and then batches of, as much as 100,000. So that's, pretty good size. All right, so that would be how many records you send. Remember that the matrix then, because it's about 40 features and one label, so it would be 4 million by 40, or in this batch size, 100,000 by 40, or if you pick the one that's 100, it would be 100 by 40. So you have to consider that. All right, the next step is, notice that we're using the built-in TensorFlow one-hot encoding function. So remember that nothing runs in TensorFlow until you create a session. So here we've created a little function, convert one-hot. We provide the data, the labels that we want to one-hot encode, and the number, which implies the number of classes. So num is going to be, in our case, 2. All right, so we take data and the number 2, and we apply tf one-hot. That creates our tensor. And to run it, we're going to create a session. Notice that we call it SS. This will be a different name from the name of the other session we're going to use for the main code. And then after that, we do SS run tensor, and we create an array here. We could have also done, to make this a little bit more intuitive, this would be the array, and then this is the tensor. And then we just return tensor. Okay? So that's our one-hot encoding function. All right, once we've done that, we will use it later. All right, so now let's look at the code. So I'm going to start, cleaning this up and discussing it. So the first thing we're going to do is, since we're using the function read CSV in the pandas library, so remember that pandas is a very efficient library for processing data. So it's not for machine learning per se, but it's a very useful tool for the data scientist. Something that might take you 200 lines of code with for loops can be done with pandas in 20 lines of code very efficiently. So I do although I'm not covering pandas in this course, I do strongly recommend that you look at pandas because it is very powerful. So we're going to use it for today. We have to provide a list of the columns that we want to slice out. So we need something. So I'm going to add a comment here. And then basically we need to say, I want columns 1, 2, 3, and so on until n, right? So that's the list that we want to create. So we're going to use this. We actually use numpy here. And we say numpy a range. And we specify that we want to range from to 41, right? So that should be to 40 here, right? And so we have that range, and that's in a variable called feature call. It's just a list that we are using, okay? Once we've created that, let's just add like a little space here. And now we're going to create another variable feature, and this will read the data with pandas. So I'm going to do pandas read CSV. Now remember, this is my file kddcup data.csv. Now you might ask yourself, how, here, even though it's 4 million, I'm only reading the data once into memory. But what if it was, billions, 4 billions? How would I read all that data? Because at that point, pandas may not be able to read it all at once. So what I would recommend is that at that point, you would need another for loop that would read, chunks of 1 billion, let's say, records at a time, right? With this, you would load it into this, and then provide that information to the TensorFlow code. And so you'd have to sort of like read data in batches into TensorFlow itself, but before you would also here in this part where you're just reading data from disk to memory, you would have to read that in batches as well. One at a time, to the maximum amount of RAM that you have, and then pass that on to TensorFlow itself. So you might have to change the code a little bit. Here we've only, to avoid complexity, we've only focused on doing batch processing on the TensorFlow part itself, and not in this part where we read the data from the hard disk to the RAM memory. All right, so we only have to do this once. So we use, again, pandas read CSV. We read the file kddcup.data.csv. All right, we specify that the delimiter is a comma, and then we specify the columns that we want to extract. So in this case, use calls is this feature call over here, right? So feature call, that's the value we have here. I'm going to add the backslash here so that we can see the data below, and so you can see we want to convert this into data type string because we still in the data set have some things that are string, and then we are using an encoding of UTF-8, so only those types of characters. So once we have defined the parameters, we're going to do pandas read CSV dot values, and that will extract the information from KDD data.csv. All right, so at this point we have our data in there, okay, for the training set. So let me add a line here. And so now the next step is we have a few parameters in the data set. So if you imagine the data set, we have column 1 or column 0, and then column 1, column 2, column 3, and so on, right? So columns 1, 2, 3, and 4 have strings. So they are actually, like they might be like ICMP, TCP, UDP, right? Those are the values in that column, in that one column, for instance. So what we want to do here is we want to use our label encoder, so that we've used label encoder before with the sklearn examples. If you remember, label encoder is the kind of function that you use when you have something like goodware malware, and you want to change that to be 0 and 1, all right? Or you have, intrusion, not intrusion, so you want to change that again to 0 and 1. So you want to encode it as a number. So you use then here our label encoder, and then we tell it fit transform, take the data that we just read in features, right? So we take the data that we just read in features over here, this variable here, right? And we're just going to say, okay, we're going to slice from feature all the rows that belong to this column. So we're going to do this in a for loop. So, we're going to take all the rows in column 1, then all the rows in column 2, then all the rows in column 3, and so on. And we're going to run label encoder on them, and then we're going to reassign them to the same feature matrix to all the rows and that given C column. So you can see C is the same here and here. So that basically allows us to take columns 1, 2, 3, and so on and encode them from being TCP, UDP, ICMP to being 0, 1, and 2. All right, so once that's done, we are ready. We can also then, if you're thinking about what this is in the pipeline, this is cleaning the data, right? So, our data was a little bit more messy this time, so we had to do a little bit more cleaning here. So the next step is also, I would describe it as a cleaning step. All right, so let me add another line here. So in this section, I'm going to take the feature, again, that we just used, right, the feature matrix, and I'm going to change all the values. So at this point, all strings have been converted to number, so everything should be, no longer strings, but numerical, and so now I'm just going to typecast it to be float. So I'm going to take the tensor, or this, object here, and convert it to all float. All right, so that's, again, just pre-processing, cleaning the data. All right, the next step is now we are ready to read in the labels. All right, so I'm going to read in the labels here. Okay, so to read the labels, it's pretty much the same thing. I'm going to call the variable target. I'm going to use pandas read CSV function. I still read KDD cup data CSV. All right, the delimiter is a comma, and I'm going to use, as you can see, my list is actually pretty simple this time. It's just column 41. It just so happens that column 41 in the data set happens to have the labels. All right, then I'm going to add, just for readability, the backslash here. And you can see here again, the data type is string, encoding is UTF, and dot value. So we read the values. So pretty much what we did before. All right, so now we have our labels and our data. All right, so the next step then is we need to do a little bit of pre-processing of the data as well. So some more. So here let's focus on this one. So I would suggest at this point, if you're looking at the video, if you're, take a minute or two and just think about what this code is doing. All right, so pause here, think about it, right? Try to figure out what this code is doing. All right. All right, so hopefully you paused the video and saw. So now, what would this be? This is, what I had described in the video before. We take a for loop in the range from 0 to the length of the vector that contains the classes, right? So we take all the labels, we count how many we have, how many entries. We're going to iterate through that, and then we're going to grab target, which is the thing that has the labels for us. We iterate through it, and we're going to say, okay, for each one, is it equal to normal? Does it contain the word normal? Now this dot, you might think it's a little strange. This was just a little dot that was there in our data set, and we could have cleaned it up, with something and just gotten rid of the dots, but everything had the dot, so normal dot became the class normal. All right, so anyway, so if we do, in this for loop, we are comparing each target to see if it contains the word normal. If it doesn't, that means that the class that it has is actually an attack. So it's going to be like denial of service, or it's going to be redirection attack, or ARP poisoning, or some kind of an attack, right? And so we decided at the beginning, as I said in the video, that we were not going to do too many classes. Instead, we just wanted to have two classes, either normal traffic or abnormal traffic, like an attack. And so every single one of these entries that says denial of service or something like that will just be changed to the word not normal. All right, and that allows us to change our data set and make it a two-class problem. Okay? Once we've done that, the next step is to do the normalization. So we're going to do our normalization here. All right, so we normalize the data. So we're going to take, again, we're still in the cleaning and preprocessing stage. We use standard scalar, SC, right? And then we fit the data into this feature set. So remember, this is when you have your X matrix and you're taking, when you have features that go from 0 to 65,000 and other features go from 1 to 3. So you want both of them to be in the same range or scale. All right, so we fit the data, and then SC transform of feature creates our new vector, and let's just call it normalize. So it's going to be feature underscore normalize. All right. Once we've completed that part, we can go to the next part here. And now we have our original target, right? This one that now contains only the words normal and not normal, right? So we have those two. If you remember, we once again used the label encoder. This time around, we want to take that target and change it from normal to not normal, or from normal and not normal. We want to change it to 0 and 1. 0 and 1. All right, and so we used our label encoder again, label encoder, fit transform target. All right, and that gives us now target label. And so now the labels are ready and pre-processed. The next step is to use the function we previously defined. Okay, so we need to one-hot encode the data. So by now you should know what one-hot encoding is. If you don't, again, I suggest you go back to the previous videos. But remember, one-hot encoding is when you have labels like, normal, not normal, 0, 1, and instead that needs to be 0. It needs to go from being this 0, right, to being that, right? So at this point, this should make sense. If it doesn't make sense, then go back to the videos, right, for one-hot encoding and try to understand that part. All right, so here we're just using that function, convert one-hot. We take target label, which is what we have here. We give it that it's 2 dimensions because there's 2 classes, and then that creates our target, which is one-hot encoded. So at this point, we are ready to proceed. All right, so we are ready to proceed. So I'm just going to do this. This is the train split. All right, train split. Now we could use various splits here because usually we've used like 70-30 or something. Since this is such a large data set, this is about 4 million records. we can make our test set a little bit smaller. So let's go ahead and say that train is going to be 90% and test is going to be 10%. Okay, so 90% and 10%. Okay, so now we proceed. These will be our data sets. So X train, X test, Y train 1 hot, Y test 1 hot. So these are the 4 matrices that we now create, which will allow us to do the training and testing. We call our function train test split. So let me move this one down. I'm going to do the backslash. Okay, and there you go. So we have train test split. We provide feature normalized. So normalize. All right. Target 1 hot, which is this one over here. So target 1 hot is that one over there. We specify the test size, 10%. Since we're dealing with big data, this would be one point where I would recommend that you try other things. Try, for instance, a split of 30%, right? Or, something like that. And see if that slows down the processing, right? Now because this is big data, you kind of have to consider other issues, and this is important, Is transferring a test set that has 250,000 records is through the network and everything like that, is that a good idea? Does that slow things down on the CPU side, etc.? Okay? But so that's something that I recommend you do. We're going to leave it at 10%. Let me add the backslash here. Okay? And so that's kind of the end. So we do test 10. Remember, random state is to randomize the data. So this is the point, whenever you get these 4 now, they're going to be randomized, right? So this is the point where you randomize them. So you can try different values here for random state, different numbers like 42, 10, etc. And see if these values actually change anything. They should change the randomization, all right, of your data set. Okay? So we're almost done and ready to do the analysis. Okay, so let's proceed here now to extract. Now, if you remember, when in one of the lectures I talked about A and B, this is a place where using A and B is very useful, right? So A and B is for extracting the features and the columns. So if you remember, X train has the number, has the train set, right? X train. So that's, you want to know the number of features. So you take X train, so this should return about 40 because it's shape 1, right? So it's the shape in the y-axis, if you will. So this is the features, which should be about 40 features or so. And go ahead and print this out, so that you convince yourself of what it is. Now this one over here, B, is the number of columns, right? So this is the number of columns. So columns, all right, so this is going to be, you take the Y train 1 hot, and you take row, the first row basically, and so that then you calculate the length. So that should be 2 because we know that there's only 2 classes here. All right, so that gives us our parameters A and B. Then after that, we just have, I'm not going to describe this function anymore. You should know by now what it is. All right, this is our print stats metrics. Remember, it takes Y test and Y pred, right? So the real labels in the test set and the predicted labels from the test set using the model, compares them and gives you everything, confusion matrix, precision, recall, and so on. Now, we're going to talk about the batch size now, and that's an important parameter. All right, so I'm going to go down here. Okay, so we talked about print stats metrics. That's taken care of. Should be pretty clear to everyone. Then we are ready to talk about the model. Okay, so we're ready to talk about the TensorFlow model. Now again, this is, we're basically using the same code that we used for the malware example. So, which is what I was saying, that once you know basically how to do one deep neural net, you really don't have to change that much. Now keep in mind, we're not doing convolutional neural networks or RNNs or anything like that. If we were doing those techniques, they would require a little bit more changes. But in our case, we're just building simple neural networks or deep neural networks of 3, 4, 5 layers. And so in that case, we don't really have to change much except the architecture. So we already built this structure that we want to use. Remember, whenever we want to use different layers, right, we have this nice this function that we define, right? If you don't remember, again, how this function works, I suggest you go back to the lectures on Chapter 4 and also the previous labs. So I'm not going to spend too much time on this. By now, you really, if you're here, you really should understand this one. But just quickly, remember that the layer is basically the function that allows you to do this. But it is so general that you can apply it when you have other layers, right? So if this is your first layer, then this is hidden layer 1, and then if you're going to create an architecture, you're going to do maybe a second layer, layer 2, which is MH1 plus B, right? So remember that this is how deep neural networks work. So you have the original X, you have a mapping with a weight vector M that creates H1, and then H1 is the input to the next layer with another weight vector that produces H2. Right? So remember that that's the key function that's taking place here to do that mapping. Just one of these mappings is done between one layer and the next layer. So that's really the logic. All right? And so really quickly then again, remember the inputs are the previous layer, right? The data, the shape of the weights, and the bias. So we have, you can play around with these parameters, but we have basically a standard deviation to use with our random normal initializer, all right? And that's W init, which whenever we create our W will be the input that we have here, W init, okay? So we do the same with bias. This is basically a constant of all zeros, and when we define our B or bias with the functions get variable, which I've already described as well in previous videos, that gives us, we use that initializer, and we specify the shapes, all right? So the shapes of this, okay? And then that just creates our matmul function, input times W plus B, and we pass that through an activation function called ReLU, which I've already discussed as well in a previous video. All right, so that's our layer, and then here really, this is where we define the architecture that we want to use. Now keep in mind, XTF is the input data, right? So we already specified that each vector is of size 40. So this will be of size 40, all right? And that's already reflected in the A, right? So A is 40. This is a vector of batch size times 40. So if we're using batch sizes of 100, this is 100 by 40, for instance. Every batch, every iteration. But it could be 100,000 by 40, all right? So that's up to us to define. So A is the number of features, B is the number of classes, and then here, again, draw this architecture, and I strongly suggest as part of the lab that you do different architectures. So in this case, for instance, I'm going to change the architecture. So this is 30, all right? So then the next one, I'm going to say, so the input here is XTF. For the next iteration, it's going to be hidden 1, right? So hidden 1, if you notice, is the previous output. So the input to the next layer is the previous output, right? And then this layer produces this output, which becomes the input to the next layer over here, so hidden 2. So let me change this. If we know that it's our original one is 40, I'm just going to make this 40 as well. So I'm going to keep all consistent at 40. So this is 40, so that means that this one is also 40. So I'm going to make this one 40, and then this is 40 because the bias is 40, okay? Remember that the bias should always match this parameter here. All right, then I'm going to do this one, and this is 40, and I'm going to make this one 40 as well. But then here, and as I said, I'm just playing around with the architecture. You could try the architecture I had before. So now let's try this one. So this one has to be 40 because it has to match with the dimensions of the previous layer. But here I'm going to make this 20. So I'm going to compress it a little bit. You know, whenever you compress something, it forces the algorithm to learn with less. So you should think of it that way. So because this layer is 20 now, then the bias needs to match it. So that's going to be 20. All right, and then the last layer, hidden output, needs to match the previous layer. So then this needs to be 20, and this 20 will be mapped to just B, where B is just 2. All right, and as I said, this is just, you know, a different kind of architecture. I suggest that at this point you try to draw this architecture by hand, and you should be able to visualize what it looks like. So that's the architecture, and that's pretty much all we have to change. So not much to change there. All right. Then these functions are exactly as we had them before. You know, we have our loss deep now. Remember, we use the built-in loss function, softmax cross entropy with logits. Okay, we just specify these parameters. All right, so we specify logits is output. Right? Remember, output is the what the inference returns, this, and then we compare that to YTF, which is the real label. So it's basically the predicted versus the actual, and that's what we're trying to minimize. Remember, again, just like in linear regression, the sum of the squared error. So y hat minus y squared, right? So that's kind of the same thing. And then that's just to reduce this, to minimize, and then this returns loss. Then we look at gradient descent. That's pretty much the same. Now, keep in mind, there's also another one called the atom optimizer. And so that's, if you check in the book, I have that function in there, atom optimizer. Basically, you just replace gradient descent with atom optimizer, and that's it. And it's supposed to be a better version of gradient descent, actually. So it should give you better results. So keep that in mind here. So I would suggest here, as part of your lab, you know, try the atom optimizer instead of gradient descent. Right? So they're both based on gradient descent, but it's just the name is different. All right, and again, just as part of your lab to get better, just to try out different things, but it's supposed to be better. All right, finally then, the eval function. This is pretty much the same one. If you're by now, you should know. Pause the video here, take this as a quiz, and just ask yourself, if I take two tensors, output and TF, which are, let's say, of 100 records by 2, right? You know, what does this function do? All right, so try to answer that question for you. You should know by now what argmax does, right? It returns, you know, so I'm not going to tell you, but, you know, you should look it up. And you should see the previous videos, etc., and, you know, as a test for yourself, you know, see what this does for you. But as you know, this function, evaluate, takes predicted and actual, compares them, and it's going to return the accuracy that we have here. All right, the next step is, again, pretty straightforward. You create the placeholders, right? XTF and YTF, they're both float, size none, because the batch size here it could be different, right? So, you know, we're going to start with 100 records, see how that goes, and then switch it up to maybe 100,000 records per batch and see how that goes. All right, so A is the number of features, right? And B is the number of classes, right? So those are the placeholders. Then we have the core functions here, just like we did before. We have our inference function, which takes the original training data, number of features, number of columns. This is our y equal mx plus b function. So output then is compared with the real output and minimized in the optimization. That cost function is returned to training, which uses gradient descent to optimize it. And so whenever we want to run our model and figure out our output function, our y equal mx plus b, we just run the node train op. Then once we want to predict, use that model, we can do so as well, right, with the created function. Right? Evaluate takes the output, again, of the function, whether with the train test or the train set or the test set, and it compares it to the actual values and returns. Now, I just described this one over here, right? So that's the function. All right, so once we've completed this, we are pretty much ready. We just have to... Now, if you notice, this code was very similar to the malware code, and it's very similar to the videos, right? So the lecture videos. So really, all that we've changed so far was the architecture. This time around, we had an architecture. I didn't change the number of layers. Actually, I still use the layers. I do suggest that in your lab, again, try fewer layers, right? So just try 2, see if you can figure that out, how that should work, but just try fewer layers, all right? In the book, I also have an example of 2 layers versus like 4 layers, but you might imagine you just get rid of the ones in the middle. All right, so that being said, we are ready to create the session. Notice this is a different session. We run init, which initializes all nodes in the computational graph with their data types, etc. YP metrics, we've already discussed this in previous videos as well. YP metrics just uses the argmax function to convert the output, the predicted y-hat function, from one hot encoded to not one hot encoded. So if you have 0, 1, 0, what is that? That is just 1. All right? So now we've completed that. Now, in a previous example, we actually ignored these 2 parameters, but this time around we need them. Given that we have, over 4 million records, and it's kind of a big data problem here, we want to read our data in batches. And so how do we do that? What we're going to need is we're going to figure out, first of all, the number of samples in the train set. So we're only going to read the train set in batches here, not the test set. So we're going to take x train, right, and we figure out its shape 0, which is the x dimension. So that tells you how many rows there are, and that basically translates into how many samples. So we got the number of samples, and then we do a little math here. So we take the number of samples and we divide it by the batch size. So if we define a batch size of 100, imagine you have 4 million, 4.8 million divided by 100. So that's going to be a lot of batches. All right? If we took 4,800,000 samples, we divided by a batch size of 100,000, then we're going to have fewer batches, right? So you have to think about how much memory you can send through the network. This computation gives us number of batches, which is what we want, all right? So if you want to convince yourself even further, go ahead and add like a print of num batches so that you can see the actual value. All right, and as you can see, that is it. Here, I'm just going to add the last part of this. So all I have left is the for loop, and the for loop is actually pretty straightforward. Oops, so I'm just going to do here print done. All right, and that would tell me that the algorithm has finished executing. So I have the last part of this is to do my for loop. All right, so my for loop is going to be for I in range n epochs, which we define to be about 1,000 epochs. So we print out this is epoch number I of n epochs. All right, that's pretty easy to understand. And now here we have our logic for the batch processing. All right, so for batch n in range num batches, so num batches, remember, is this value. Currently, we have a lot of batches because our batch size is only 100 samples. All right, so given that, we're going to calculate standard in n. We've already discussed these in the lecture, right, if you remember. So that's the first batch is 0. So then it would be 0 times batch size, which is 100. So start would be 0. And then n would be 0 plus batch size, which is 100, so n would be 100. So that means we are going to slice from 0 to 100. Next iteration, batch n is 1, so that would be 1 times batch size, so that's 100. So start is 100, and then n is going to be 100 plus 100, that's 200. So we slice the next batch from 100 to 200, and so on, the next one from 200 to 300, and so on. All right, depending on the batch size that we define, right? Once we have that, we can proceed to train our model. So very easily, we can do session run. Remember, this is where we run the session. We only need to run train op. All right, so we run train op. We provide the feed dictionary, right? I've already discussed what the feed dictionary is. Way to pass our data. And notice here, we are passing our data to our nodes XTF and YTF. Okay, let me add the backslash here and move this down. If you notice, what's important here is that we are reading the data for TensorFlow in batches. So we are reading the data in batches. So since we're reading the data in batches here, that saves us in the training. So this is the great mechanism that TensorFlow has that allows you to build very complex models without giving it 4 million records at a time, right? So this is what I've been saying, that TensorFlow is built to handle big data because, okay, this is 4 million, but what if it was 4 billion or even more, right? So this same mechanism allows us to, the algorithm will not stop. It'll just keep taking the batches and it'll keep updating the model and learning and learning and learning. All right, so that's where the trick comes in as far as, reading data in batches and making something that is really large efficient to process. All right, so you can see here that to assign our data to XTF, we take XTrain and slice standard and n, right? So we slice basically all the rows from 0, that meet this criteria, from 0 to 100, 100 to 200, and so on. And then the same applies here for the Y-train. We do the same. Now we feed in only the vectors that from start to end, right? So we're slicing those out in batches and assigning them to XTF and YTF. All right, so that's that's pretty much it as far as the the big data issues. After that, it's very straightforward, just like we did before. Let me move this down. So print a line. We print the accuracy score, which is going to be, let me get rid of this one actually. The last part is we want to run now so we ran the session for the train set. Now we want to run the session for the test set. So just like we did before in our lectures or in our videos, we get result and we get Y result metrics, right? That's basically taking the session, running eval op, right? Eval op and running YP metrics. Both of these return the predicted classes, if you remember. So we're running this one, evaluate, because that is eval op. That's eval op there. And we are running YP metrics, which is basically just grabbing output, which means grabbing this output here from the inference function. Okay? So now I can scroll back to the session. I do eval op YP metrics, right? I run both of these. Notice that in the feed dictionary here, because this data set is only 100, it's not 100,000. It's out of 4 million. It should be about 400,000 records. So it's something that's not big enough, so we didn't read this in batches. But basically, we just give it our Y test 1 hot and our X test 1 hot. Okay? And again, we give those XTF and YTF, the nodes in our computational graph. All right, and we obtain these results. And then finally, we print out result here. And we take the Y test 1 hot, which is the real data. Right? We apply our argmax function, and we get Y true. To keep this a little bit consistent with everything else, I'm just going to add Y pred here, and that's going to be equal to Y result metrics, right? And so that then is going to be Y pred in here, right? So all we're doing is in our print stats metrics function, we are comparing Y true with Y pred. As you can see, this is very similar to what we did before, but now we did a few changes for batch processing, a little bit of change in the architecture, but that's pretty much it. We still have a deep neural network with about 4 hidden layers. So basically, let's look at the parameters. The learning rate is 0.01. We're going to do 1,000 epochs, and the batch size is 100. Right? So let's see, for the training set, let's see how this performs. So now I'm just going to run my Python. Right? So let's do Python All right, seems to be doing its thing. All right, so you might want to pause the video soon when you see the GPU CUDA information. Remember, by default, this environment will run the GPU, not the CPU. But if you notice, we barely had to do anything in the code, right? So it just grabbed that processor by default, right? So it's loading. There you go. So it did the calculations and it did everything. All right. So the TensorFlow has finished. The code finished. This is it got to its epic 999 out of 1,000, right? So it has completed the training, and then now we can do the analysis of the results. Again, these are just the same performance metrics that we've been using. You can see the accuracy is basically 100%. You can see in the confusion matrix, out of almost 400,000 test samples, right, that we have here, a lot of test samples. A lot of them are correctly classified, right? So if it's out of 97,321, there were only 109 misclassifications, and then out of 392,522, there were only 149 misclassifications, right? So we had a total of 489,000 samples in our 489,843 samples in our test set. So you can see the precision, recall, and F measure are really good, almost perfect. This was obviously a very easy data set, just kind of for academic purposes, for big data analysis. But obviously with more complex data sets, you might expect results that are not this good. So other things that I suggest that you do for this lab, if you're an instructor, you saw how we only use two classes, normal and not normal, right? But you could also say normal and then all the different attacks, and so you'd have multiple classes, right? Several classes, and so you might want to try that. Obviously, your misclassification errors are going to go up because it's a little bit more of a complicated problem. But anyway, that concludes our big data NSL-KDD lab. This was again for intrusion detection between normal and attack network traffic, right? So that's, as you can see, it does pretty well, and that concludes our video.